Hello, everyone. So today we're going to be essentially wrapping up mass balance by comparing some of the techniques that we've used so far and showing how we can bring them all together. So last time we finished up looking at molecular and atomic balances. Now, what I wanted to go ahead and talk about is that we've got three major techniques that we can use to describe a reactive chemical system. We have our good old friend from chemistry, the ice table, molecular balance, and atomic balance. Now, I want to go through the strengths and weaknesses for each of these. The biggest thing is the ice table. It only works for one reaction system, so where I only have a single chemical reaction. Molecular balances and atomic balances, in comparison, can deal with systems where two, three, or even four reactions are all taking place at once. Similarly, it also requires that you know what reactions are taking place, but it's very easy. So if you can use it, it's great, it's simple. However, you also have the molecular balance. This also requires you know what reactions are taking place because you need to know what molecules are being consumed, what molecules are being produced, and relatively at what rates. Uh, However, this does allow for easy linking of molecular systems because you can see which molecules are consumed and which molecules are produced in any given reaction. The atomic balance, however, can actually be performed where you have no knowledge of what reactions are taking place, where essentially it's a great big mystery. In that sense, it's very general. However, it does include a lot of conversions between molecular and atomic systems. So we have to go through moles of molecules to moles of atoms and back quite frequently, which can get a little bit messy. But if you're not sure of if you're not sure if you can use an ice table or molecular balance, atomic balance is general enough, it almost always works. Now, when we were looking at these reactive balances, one of the things we did was we were just looking at the unit process. But it's important to know that unit processes never occur in isolation because we often are combining these with at least one unit operation, sometimes several, especially when you include things like mixing. And so we need to figure out how a reactor is embedded in a larger industrial process. And we'll talk about this more towards the end of the class. But one of the things we have to account for is going to be things like mixing before reactions and processing after, as well as sometimes things like purifying feeds. So let's go ahead and look at a simple combination system. Let's say I've got a reaction that's fairly inefficient. Well, you can improve this reaction by putting a separator afterwards and taking the unreacted starting materials and recycling it back through. You can use this to greatly improve the efficiency of a system. So let's go ahead and look at one of these systems. But one of the things you should be very aware of when solving one of these problems is that choosing the order of which balance you're doing can actually be very important. So for in this case, we've got four major balances we can be concerned with: a mixing, a reaction, a separation, and total. So we're going to want to be very cautious about how we handle any given problem. So let's bring this a little bit away from the general and more towards the specific. Let's take another look at a syngas process. So let's go ahead and see how we can generate syngas by reacting methane with water in steam reforming. So as some of you may know, this is one of my favorite reactions as it is a popular way to generate hydrogen gas. So let's say I take a feed that is 50-50 in methane and water. So in this case, my feed is the exact stoichiometric ratio of methane and water. And I want to go ahead and figure out how much methane, CO, water, and H2 I produce, as well as the overall reaction efficiency. Now, one of the ways we can help improve the efficiency of my reaction is by taking some of my excess water and methane and recycling it back through. But it is always worth noting that any separator is never perfect. So some methane and water will almost always make it through. So let's go ahead and try and find the composition of, each stream in this process. Both my direct feed, direct product, recycle, as well as the overall product. If I have an overall conversion, so based on starting materials and end product of 95%, and that 92% of the methane and 60% of the water are separated out from using this permeator, which is essentially a fine filter. So of the methane coming through, 92% of it ends up in the recycle, and of the water, 60% ends up in the recycle. So this is actually going to be a bit of a tricky system. We're also going to want to try and figure out the percent conversion or the efficiency of the reactor itself, and not just the overall process. So this is one of those tricky things where I've got a lot of moving parts to this system. So we already accomplished the first step of running a mass balance, which is we diagrammed out the system. And this really helps us identify what we know and what we don't know. So the next step is going to be trying to set a basis. Well, since we've got a percentage basis on my starting materials, let's go ahead and set an overall total to make my numbers convenient. So I like a nice basis of, say, 100 moles per hour of total reactant, so of feed entering the system. And using this, I can quickly determine that I've got 50 moles per hour of methane and 50 moles per hour of water entering the system. And then using this, I can try and solve my, my output rates using this 95% conversion percentage. So using this number, I can say, all right, if I've got a 95% conversion, that means via stoichiometric ratios, 90% of the 5% of the methane has been turned into CO. So I'll take my methane numbers, 50 moles per hour times 0.95, and we end up with a 47.5 moles per hour of my methane product, or my carbon monoxide product. I also am going to have a 95% conversion on both methane and water, as they are co-limiting. So times that by 0.05, and I'm going to have 2.5 moles per hour of both water and methane. And that leaves me one last reactant, H2. Well, I'm going to have 3 times as much H2 as I will carbon monoxide, just again based on stoichiometric coefficients. And you can run this again either through a mass balance or an atomic balance to really show that this will be the case. Now, one of the things is that these numbers themselves don't actually mean much, because my choice of a basis of 100 moles per hour was artificial. So what I can do is add these together to get 195 moles per hour total product stream. So one of the things to make note of, because this is a cleavage reaction where I have more products than reactants, it shouldn't be too surprising that the moles of products is actually almost twice that of the moles of my reactants. And then using the moles of each individual component and the total, we find that we have about 24% of my output is carbon monoxide, about 1.3% of it is methane and water respectively, and most of my product, a little over 70% is going to be hydrogen, which again is usually what we're after in a steam reforming reaction. However, this isn't all we wanted to figure out. So now I've got my reactants and products, but I also want to go ahead and figure out what the composition of my recycle stream is, as well as my direct reactants and direct products. So let's go ahead and try and focus a little bit more on that recycle stream. So we want to figure out how much methane and water is in these streams. So what we're going to be making use of now is the fact that I've got 92% of my methane from here ends up in my recycle stream, which is another way of saying 8% of this methane ends up here. So I know that the direct methane product times 8% is going to be 2.5, which means that in this direct product stream, I've got about 31.25 moles per hour, so a fairly large rate of methane production, which again means that the remainder of this is going to end up in the recycle stream. So we can simply take the difference of whatever methane is produced but doesn't end up at the end product is going to end up at the recycle. And that's about 98.75 moles per hour. So again, most of the direct product ends up in the recycle stream. We can do a similar process for water. About 40% of my water makes it through the permeator, which we also know is equal to 2.5, which means in my direct product stream, I only have about 6.25 moles per hour of water. So actually not that much water compared to my methane. And again, we can use the difference as figuring out what's in the recycle. So again, 3.75. So most of my recycle is going to be methane with a little bit of water along for the ride. And you can imagine one of the reasons why this will be the case is water's a little bit more stickier, so it's probably going to be hanging on to the carbon monoxide a little bit better. The nonpolar methanes probably goes straight through my permeator, but also the fact that we're going to want to do our best to recycle the more expensive material, which is the natural gas. Now, in order to determine the yield of the reactor, I'm going to need to figure out how much methane is essentially in the direct feed, and we've already determined the amount of methane in my direct product. So if I know the amount of methane here and here, congratulations, I now know the amount of methane here. So it's going to be 50 plus the 31.25 we determined earlier, for a total of 81.5 moles per hour coming in through the direct product, through the direct feed. And the direct product has about 47, and the direct product, which is carbon monoxide, has a yield of about 47.5 moles per hour. So when we turn this into a percent yield basis, we end up with a percent yield of about 58.5%. So this is actually a fairly useful illustration of a common principle in industrial chemistry. Because this overall reaction or overall process has a yield or percent conversion of about 95%. This is very good. The reactor, not so good, closer to 58%. One of the quickest tricks you can use to improve the yield of a bad reaction is making use of recycle streams. And it more or less ends up working by essentially letting product through and keeping on recycling the reactants until eventually, even if it takes 5 or 6 cycles, they end up being converted. So in the real world, this is one of the quick ways you can use to make a better system. So that brings us to the end of mass balance. Next week, we're going to be picking up energy balance. Same general ideas, except for we're doing it with energy instead of substance. Till then, take care.